It just occurred to me I have something for you as well. Here you go. Well, I think we can get started. Welcome back, everyone. Hopefully we get some more people in before we get too far in. We're in section 1.7, where linear algebra started to get pretty interesting, I'd say, right around this part in the course. Linear independence is the topic we're going to need right before we begin to define linear transformations. These are going to be functions that take as an input a vector from a vector space and output another vector into possibly a different vector space. So we're looking at bigger and bigger ideas the further we go in the course. And also linear dependence ties in together finally with the basis of a vector space. This is some ideas we'll be looking into in chapter 4, once we fully and formally define what we even mean when we say vector spaces. But the good news is already we're in week 4. The work we've been doing is in vector spaces like R2, R3, R4, and so on. So we're getting all of that intuition in just more familiar places. So our section 1.7 is going to be a pretty pivotal section as well, since this is the last one that's going to actually appear on the first exam. We'll also cover section 1.8 next class, so we don't get so far behind on the schedule. But I feel like the 1.8 section would just be too close to actually take an exam to be really a real good section to put on there. As far as 1.7 goes, if you see a section like this thrown on the exam on the very next week, you can regard the questions from 1.7 as being kind of the more basic type of questions. So that'd be questions would be really great if you were attended class, worked through the homework and that kind of stuff. These kinds of questions are the ones where you've had the opportunity to see them, get your feedback from the homework and that kind of stuff. So it's going to be more standard kind of exam questions on the last set. And so, by the way, what are the standard exam questions? You could look here for a sample exam 1 problems. Things. And it just goes on a sections by section basis. It's the ordinary lecture notes, but I took out all the definitions, all the theorems. It's now one big worksheet. If you can still solve these problems, then you're on really great track for completing the first exam without any kind of issues. These really are the typical exam questions that you can expect. If you'd like additional practice, then you can come down here. And there's even more questions. This is kind of an older document, but I felt like, I mean, it's still in your algebra, and if you want more problems, probably you wouldn't want to print it out, but this is a review for the entire course. So you can target a section by section. It's a little bit more, I'd say, there's less questions there, but it's still going to be a helpful resource if you want to go through this one. This one has answers on the very, very back. If something just looks weird on the explanation, don't hesitate to ask. Because it's an older set of notes, some of these are solved in slightly different ways. As far as this document goes for the review, since these are just the same exact problems from the lecture notes, you can go up to the Moodle resource, just kind of scroll through there and open up one of those sections. That would be the actual solutions for those problems. I've talked quite a lot about the exam, so I'll turn it over to the class. Any questions that you folks have so far about upcoming exam 1?
Are we gonna have a lesson after the exam?
It'll be just the exam on that day. And that's a good thing you asked. When it comes to writing out this exam, I do try to bake in about 15 minutes for just checking your answers on these kinds of things. So we typically take most of the class time, but if you finished early, you don't have to stay. Yeah.
Are you gonna provide the theorems on there? Do we need to memorize the theorems before we start?
There's some theorems that we're going to have to memorize, but you're going to find those are the things that we use like all the time. For example, if you open up this exam 1 formula sheet, these are the ones that you don't necessarily have to memorize verbatim. So you can call on this theorem right here if you need to. It's about consistency and uniqueness. And this is the big theorem that relates a lot of different objects in linear algebra. I feel like this one is a pretty hard one to just have in your head while you're taking an exam. That's pretty much how we're going to do the exams. Anything that's like a technical theorem like this stuff, we throw on there. And anything that's more along the lines of, say, let's go to maybe section 1.3 to illustrate. Things like these, for example, well, you should have them memorized, but not necessarily verbatim. You've noticed when you do this problem, you didn't necessarily look up vector addition or scalar multiplication, nor any of those algebraic properties we take for granted. That's the kind of stuff you wouldn't necessarily try to memorize for the exam. We go over to, say, this kind of stuff, linear combinations, or this kind of stuff, spanning, what it looks like as a set. Those are the things that we really do have to memorize. Those are the major portions of the linear algebra itself. Does that help a bit with the question on what to memorize and that and such? Awesome. Another thing you can do is, as you're solving your homework problems, or looking back on them as they were handed back to you, think about what idea did I actually have to look up? Was it a definition like this? Was it any of these two? If it's on this list, you don't have to memorize it for exam one. But if it's something else, then it's something that you do have to memorize for the purpose of the exams. Also, this is the literal sheet that will be on exam one. It'll be formatted exactly like that. You can tear it off, use it for scratch paper on the back, solve your exam side by side with it, and that kind of stuff. Other questions so far, folks, about the upcoming exam one? This one is going to be closed notes. Instead, will be the formula sheets that are going to be provided on each exam. Other questions so far? How about for folks over on Zoom? Any questions that you all have at the moment? Oh, we've got some chats coming through. Pren asks if we live in Pocatello, is there a place we can go to take the exam? For this class, it was really designed with the intention that everyone would take it physically here in the classroom. And I talked to the department chair a little bit after the class got started when I realized maybe about half of us are actually on the Pocatello campus. We'll be able to find a way to arrange for you to take the exam on the Pocatello Testing Center. If you can, send me an email as soon as possible, maybe after class or during class right now, if you don't mind, and we'll make sure we can arrange that for you. Does that make sense for that question there, Pren? Awesome, thanks. Yeah, we'll get these sorted out for sure. Other questions from Zoom about the upcoming exam or otherwise? Or really anyone at this point? Okay, well, the first exam is usually the scariest one for the class because we're getting used to what would exam questions even look like in linear algebra setting. My exams, what I write for linear algebra, they look long. They're going to be 20 questions for exam 1, 2, and 3. And I know that sounds terrible, but on a real exam, there are more concept questions in a linear algebra class than there are big computations, like a whole bunch of row reductions. On exam 1, you might have to row reduce here and there, but it's not going to be on every single problem. Let me show you what would be problems that I really did ask in the past. I don't ask this one on every single exam one, but I have thrown questions like this on exam one. It's an honest concept question. If you could determine that something is linear and where it becomes nonlinear, that's a question that could be one of the 20 on the exam. For another concept question, let's take a look at maybe 1, 2, and 1, 3. Oh, what the heck? Let's go through all of them just to point them out. So on section 1.2, this is a pretty fast concept question that you can expect. Knowing the difference between echelon form and row reduced echelon form is extremely important. And so these form great questions. Let's see here. Row reduce, do not row reduce to echelon form. That could be a decent question all on its own. Stuff like this can be exam questions, but I tailor the row reduction so it's not extreme. It'd be a row reduction that you could finish in a reasonable amount of steps, no bad numbers, no crazy fractions. Some of them might be row reductions you finish in literally just 3 steps, make a conclusion. There won't be a lot of those kind of problems because then it would be too long of an exam, but row reduction does have its place on the exams. Then let's go to the next section for a concept question. I probably wouldn't ask that one. That one is like a getting started kind of question of determining when vectors are equal. But we need to know about algebraic methods with vectors. And so this has been a question in the past. We need to know how to do and calculate a linear combination. Questions about These are very common. Knowing how to take a vector equation and write out the system of equations, or taking a system of equations and writing out the vector equation or the matrix equation, not necessarily the augmented matrix. We can go from these equations to a vector equation to a matrix equation. That's another important salient feature of linear algebra. And it's a fast problem as a concept question. And even though we're not writing these down, you can always go to the recording for a quick look over of what exam questions really look like in this course. Let's see. For another question, determine the phi is a linear combination of those vectors. That could be one of those questions I would ask, but I am very careful with those questions because as you observe, there's a lot of row reduction going on there. I don't want to overwhelm the exam with too much of that stuff. Other questions on this section could be a definition kind of question. Let's write one down here to show you what that might look like. On exams, sometimes I write down these kinds of questions, especially if it's something we ever call the core definition or anything we put here is pretty much a plethora of exam questions. Every one of those definitions are massively important to linear algebra, and so we have to have a good working knowledge of them. So going back to focusing on just this one, hard to get that, rotate right back, there it is. For the spanning question, here's what an exam question could look like. It might be along the lines of a statement that says complete, or let's say, fill in the blanks. Where the blanks are, or the statement would be span V1, V2 equals some long blank would go right here, and we might put in C1, C2 in R. So if you know what goes right here now, that's the entire exam question. It would be this. C1V1 plus C2V2 would go directly inside there. And that's a concept question tied together with spanning. Does that make sense about those style of questions so far? Awesome. And one of the things that I think would be pretty worthy for us is, let's see here. Sorry, kind of lost my train of thought, but let's keep on going through these. On some of the problems, you should expect to do these kind of computations where it's going to be a matrix times a vector. That could be a whole question on its own. And watch out for these. We might be asked to explain why something is undefined, but we gave some indications of pretty much all you have to do there. Show the size of the matrix and the vector and show where it has been caused to be undefined. That would be a perfectly good explanation. So again, there's a lot of tiny little concepts that have huge, huge importance in linear algebra. And that's why exams in this class sometimes feel a lot different than other exams. There'll be 20 questions, but there are 20 concepts where getting through all the homework, they're things that you've been faced with over and over again, and that we've also been highlighting throughout the course. Let's see here. Continue to go through these. I think I'm starting to run out of concepts. I think any question, however, that involves theorem 4 is a pretty technical question. This was not a question where you're expected to be ready to go with on exam 1 and just know this completely pat. And that's why I'll make real sure on exams that I always indicate this right here. The actual notes that'll be provided on the exam. If you see this provided and you go to solve your exam 1, you'll know that somewhere, at least in one question, probably multiple questions, you're going to use this theorem. And so it's also a hint that this is important for whichever question seems a little bit mysterious. Take a look at the theorem and it might just resolve it. Well, I think that's a pretty decent enough spiel about what the questions will look like. Any questions or comments at the moment, folks? Okay, so essentially to reiterate after going through all those documents, this document right here is probably the most important document for studying, but it's not the only document. I'd say it's equally important to your homework questions as well. When you get your homework back and you see the feedback on the grading, pay special attention to that. It'll help you with your studying. And so going through your homework again, going through the old lecture notes again, going through the reading again, are all great habits for getting prepared for our upcoming exam. Well, any last questions, folks, about exams or otherwise? Yeah, I'd say go to the recording, and pretty much all we were saying is what the exam questions are going to look like. There are going to be lots of concept kind of questions. Oh, gotcha. Yeah, Tuesday, February 6th. And now that you pointed that out, thanks for that. Don't forget, you're also allowed a calculator. And it's not because I'm going to write questions that require a calculator. If you feel like that's a comfort that you would like, definitely bring it. There's only two allowable calculators, either this one, the basic TI-30XA, or if you want something with a little bit more comfort features, a better display, you could do the TI-30X2S. That's the one I typically would use. But I write exams that really it's the same kind of arithmetic you would have saw in the notes. And the moment some of these problems get a little bit nasty, I do proofread my exams. I change the numbers so the calculator is not the most important thing. It's more just a comfort if you decide you'd like to have one. I've talked for about 15 minutes. I think that's the major concepts I wanted to talk about or comments I want to make on the exam. Any other questions so far, folks? Okay, last thing to mention, just to reiterate, section 1.7 is on this exam. The due date is standard of 1 week turnaround, but these due dates are really just for pacing. What I would encourage you to do is solve assignment 6 as fast as you can in your schedule, email it to me or hand it in physically on Thursday's class. And I'm going to try to grade section 1.7 assignment 6 as soon as possible. So I'll grade them over the weekend. I'll be emailing them back to you over the weekend. And even if you say had a hard copy, you can just take pictures of that, email it to me, and you'll get your feedback. That way, if you want your feedback on assignment 6, you'll have it for section 1.7, which is on exam 1. But just to reiterate another comment, I'm going to ask the pretty basic questions from 1.7 on our upcoming exam 1, since I know that's one is a fast turnaround. Well, let's take a look at what we are doing in section 1.7. First, this entire block of text was stolen from section 1.5 because now it's directly related to what we're about to do. In order to define linear independence, we're always talking about a homogeneous equation, which means we have a zero vector on the right-hand side of that system of equations, or the matrix equation that we see there, or the vector equation. Notice that's exactly what you're dealing with in these two definitions down here. These are always going to be homogeneous equations. So we know that the trivial solution always exists when we solve that kind of equation. But what we're really looking for is whether or not there exists a non-trivial solution. That's what's directly tied in with the new definitions. If we have a non-trivial solution, that means you can put a vector x here that does not consist entirely of zeros. At least one of the entries is non-zero. Look at the language here. At least one of the entries in the vector equation is not zero, means we have linear dependence. So the existence of non-trivial solutions means linear dependence. Let's also say a little bit more here. Linear dependence means non-trivial solutions. But we know even more, if there's non-trivial solutions, we can say something about the variable of the system. It has to have at least one free variable in order for those non-trivial solutions to exist. So linear dependence is tied together with non-trivial solutions and with, lost my train of thought there. What was I about to say? So we had non-trivial solutions for linear dependence. Oh, free variable, sorry, completely lost that thought. So it's also tied together with a free variable. If we turn it all around, we might ask, what if there is only the trivial solution, nothing else? That's linear independence. And we really like linear independence. It's how we are going to form a basis later on. If our vectors are dependent, they cannot form a basis. So linear independence says the only possible way you're solving this equation is by literally dropping in a zero for every one of the entries, x1 through xp. In other words, you only had the trivial solution x equals 0, meaning this means here we have no free variable. In the situation of only the trivial solution, that means every single variable in the system was a basic variable. There was pivots in every single column, aside from the far right one. So that's our two definitions. They're tough definitions, to be completely honest. So part of our work here in section 1.7 is to see how to adapt these definitions in a way that makes the questions we're going to ask on the homework and exams a little bit more easy to get through. This is essentially right here our goal. This is pretty much an exam one question as well, just visually inspecting and telling which vectors are independent or dependent. We'll find a lot of tools to make that happen. And what's going to happen a little bit as well is we'll stop using this definition for a little while, but then it comes back really, really aggressively on us, and it comes back in chapter 4. That's such an infamous chapter. So let's make a really quick comment here. In chapter 4, we must sometimes use this definition directly. This is the only way to find dependence for certain kinds of vector spaces, because we can have vector spaces that don't necessarily look like R2. They could be function spaces. They could be wild abstract objects. And if we're defining independence and dependence, it has to be through the vector equations for those kinds of spaces. Well, any questions at all, folks, with our core definitions, independence and dependence? Okay, here's how you can imagine what we're getting after. We're solving equations that look like AX equals 0. We're wondering if there's a free variable. If there's none, the columns of A are linearly independent. But if this system here did have a free variable, we would say the columns of A are linearly dependent instead. Now it brings us down to the 0 vector in R2. We need to decide for the 0 vector alone, is that one independent or dependent? Honestly, a confusing question. Any volunteers for a pot shot on that one?
Independent.
Anyone else? It's either independent or dependent. I don't want to spoil the beans too fast. Some for dependent. How about anyone over Zoom? Any gut reactions? Independent or dependent for 0 vector? If you're not sure, that's completely okay. It's honestly really hard to tell. And the reason I ask that is that's the use of these definitions right here. The best way to tell is just to work through it. First thing you want to do is write down the 0 vector. So the 0 vector is commonly denoted by Z for 0. Let's use that notation. It could be written this way, but if you want to exhibit it really lives in R2, you might write it this way. So there's the 0 vector. Now, if we're going to test for independence or dependence, it boils down to these matrix equations. Both times, it's the same matrix equation we're considering, whether you call the scalars x1 or c1. So let's do that. Let's take an x1 times z and set it equal to the right-hand side. This has to be a homogeneous equation, much like these. So we throw the 0 vector over there. Now we're trying to solve this system. It's a little bit easier to solve it if we expand things out a little bit more. So let's rewrite x1 times 0, 0 equals 0, 0. If we do the scalar multiplication right here, we would have, well, just 0 times 0 right here. Nothing really magical happens. But now we can see a solution for x1. Anyone see what a solution could be? Would you all agree 0 could work as a solution? Absolutely, right? If you put a 0 here, it's just 0 times 0, 0 times 0. They equate to 0. This one's the one that's not as interesting. That's the trivial solution. But now, you could put something else in there. You could put 5 in there, it would work, right? It'd be 5 times 0 equating to 0, 5 times 0 equating to 0. We just found a non-trivial solution. We look up the definitions. It says your set of vectors, even if it's just one vector, is linearly dependent if there exist weights. That's the weight or scalar, just one of them. Not all 0, such that the linear combination holds or is consistent. We just found one right here, which is not 0, which makes the original equation consistent. And this finally tells us So it's kind of tricky to see right away. By the core definition, what it says right here, Z is linearly dependent. So our first vector to consider, definitely it should be the zero vector. This one is dependent on its own. Any questions, folks, about that so far? Okay, so the linear dependence of the zero vector had all to do about that. There is a way to solve that equation that doesn't involve strictly just zero. For those vectors, we'll always consider them to be dependent. Now let's turn this around just a little bit. Suppose we're looking at that vector. Again, let's just take a prediction. It's always good to try and imagine what it should be. What would you all say? For that vector there, is it independent or dependent? Well, we have a chat over Zoom. Rajab says independent. Thanks for contributing that, Rajab. Other folks? Some in class are nodding yes, seems independent. And I absolutely agree with you. This one turns out to be linearly independent, but let's explain it as we go. This one was dependent, and already we have a kind of dichotomy. If you're talking about just one vector, dependence means you're dealing with a zero vector. Independence means your vector is non-zero. You could have a zero entry, but non-zero means there should be at least one non-zero entry there. But let's see if we can work this one out with the definition above. Really, our goal in this section is not to work out these problems in this kind of way. Our goal is to use that as a tool. And so we'll be doing problems further down the notes, addressing all these vector equations, once again, once we have these more powerful tools at our disposal. But the good way to learn this is through the definition first, because this definition doesn't go away. It's important in chapter 4. We're really, in some sense, looking at it early and seeing how things fall together. So to determine independence or dependence of this one, we do the same thing. We have to form a homogeneous equation. So we'll take x1, seems silly, but really x1 just to match the pattern here. Multiply it by the vector v, set it to the zero vector. We are very interested in non-trivial solutions if they exist to this. So let's see just what can happen. First thing you can do is expand that out. We have x1 multiplying 140. Expand out the right-hand side. It's a zero vector, but because of equality here, we interpret this in context as in R3. So 0, 0, and 0. If we move this out a little bit further, let's do the scalar multiplication here. We would get x1, 4x1, and 0. Let me fix that penmanship a little bit. This is set to 0, 0, 0. Now we're dealing with the definition of vector equality. There's only one way this is true. That's if our first entries equate. So this implies x1 is 0. Our second entries have to equate. So 4 times x1 has to be 0. And there's no new information here. They're already equated to each other, so we don't worry about it. However, when we come over here, it's already solved. We said directly x1 is 0. There's nothing else you can do here to make this equation correct. You have to set x1 to 0. And that means this has only the trivial solution. And every time we have only the trivial solution, we say linear independence in this situation. So we can now say V is linearly independent. So we did it, folks. That's the complete situation if you're dealing with one vector. If you'll see the zero vector you're dealing with, you have linear dependence, since over here, forgot to tie together that thought. This one is the non-trivial solution. If it's a single vector with one entry at least non-zero, you automatically have linear independence. Let's get rid of that there. And here's the related theorem. So now if we ever encounter these problems again, say, if this was a homework question or an exam question, I would say yes, because it's not the zero vector and you're pretty much done. But watch out for these theorems. These theorems are actually kind of dangerous in this class. So I try to highlight and put in bold and in italics the portion that we have to be very, very careful with. You really have to have exactly one vector to use this theorem. So if that's your vector, one vector in a set, you have independence if and only if it's not the zero vector. Because that if and only if logic goes both ways. And if you negate one side, call it dependence here, we'd say if and only if V is the zero vector. So it's really two statements in one. Any questions at all, folks, with this situation with a single vector? Okay, well, now we have to bump this up. We need to go for two vectors, and that's a new situation. There's really a trichotomy. We have a set of theorems for one vector, for two vectors, and then three or more vectors has its own different process that we have to use. So let's take the definition with us so we know what we're getting into. And down below here, now it's the two vector situation. Now these questions are honestly pretty hard to tell right away unless we know the tricks. But it's always fun to kind of give a guess, a prediction on these. We wonder, are these linearly independent? Let me show you something that's striking to me about the vectors. If you multiply the entry 1 here by -2, you get the -4 on the other side. And if you multiply that entry by the same value, -2, you would get +6. In a certain sense, that vector depended on this one because you just double this one to get that one. With that in mind, would you call these vectors independent or dependent? Good call. These ones are absolutely dependent vectors. We just have a feeling they should be dependent. Really, the honest 100% true proof is if it's dependent, we should be able to write down a dependence relation because we would have been able to find a free variable in the homogeneous system. Let's see if we can do that. So before I break stuff, let's try this out. So I'm thinking this equation here, I'm going to use x1, x2. The scalars are irrelevant, however you'd like to name them, and x's just make sense. Let's call this v1 and v2. So the system is x1, v1 plus x2, v2 equals a zero vector. So this is the thing we're considering, but we made an important observation even before that. We noticed you could double v1 to get v2. Let's start there. 2v1 is equal to v2. Let's double check. That's because double the first entry. Oh, that's not quite right. Good to always double check these things. -2 times v1 on the first entry would give us a -4. -2 times that would give us the +6. That's a nice equation. You could subtract v2 from both sides. Get -2 v1 minus v2 is now set to the zero vector. And the moment we've done that, we have found not only a dependence relation, we found the non-trivial solution. x1 should be -2 and x2 should be -1. I should say that differently. We found a non-trivial solution. There are now infinitely many more. So x1 equals -2, x2 equals -1 is a non-trivial solution. That immediately implies if you have non-trivial solutions, there's free variables somewhere in the system. You have a dependence relation, but let's follow the arrows there. Big thing we want to say is those vectors are dependent. v1, comma v2 is linearly dependent. We've got it, folks. We don't always want to work this way. We want to be able to just eyeball it. It's a valid mathematical tactic here. And just by visual inspection, decide if you have independence or not. Let's try this again on part B, but let's also take a peek at the theorem that's going to work for us. The theorem that we're really using is this one right here. If you have two vectors Now, this is specific. This does not work for three vectors. We have to use a different process. But for exactly two vectors, you have dependence if and only if one of the vectors is a multiple of the other, non-zero multiple. That's what we found right here. And you might have just said V1, V2. Let me write it this way, V1 and V2 are multiples of each other, meaning non-zero multiples. Now, if we look at these two, well, the only way you're going from the first vector, 1, 5, to the second one is if you multiplied by 10 in front. But then if you multiplied by 10, this 5 would have turned into a 50. We already just looked at visually and found they're not multiples of each other. These ones would be linearly independent, guaranteed. Let's write this out. If that's your V1 and V2, V1 and V2 are not multiples of each other. And so V1 comma V2 is linearly independent. So that's the conclusion on this one here for part B. So two vectors and one vector, these are pretty fast to determine just by visual inspection if we have independence or dependence. Any questions at all, folks, on these two so far?
I do have a question. So in this case, if we solve for the linear equation, is that also a solution to find out that if it's dependent or independent?
Yeah, absolutely. So let's take a look at that. Thanks for mentioning that suggestion there. Another approach would have been to do the following. And in fact, this is going to turn out into the approach that we really would take if there are three vectors, because then this idea is off the table for us. So for another approach, we can say, grab a matrix A, throw inside there V1, V2. This would be 1, 5, 10, 0. Now we could do some row reductions on this and go from 110, multiply row 1 by -5, add to the row below, and we'll get 0, -50. But notice what we've just found. There's a pivot here and a pivot here. This means AX set to the 0 vector has no free variable. And then we would conclude just immediately, this implies the columns of A are linearly independent. So that's a very valid approach for these. And it's in fact the approach we'll take for three vectors essentially all the time. Does that answer your question there you were asking about?
Yes, it does. Thank you.
Yep, you bet. Other questions at the moment? Okay, well, let's now go to that new situation. So observe for these vectors, it's very problematic if we're thinking in terms of the old theorems above. The presence of a non-zero vector does not mean the whole set of vectors, v1, v2, v3, is linearly independent. We're thinking of these as an entire set, not just one vector independent of each other. Shouldn't use that word, independent of each other. So we can't use this either, because if we're trying to deal with linear dependence with two vectors, well, in some sense you could, but you have to look at every pairwise comparison of the two vectors, show they're not multiples of each other. Then you have to go even further. You have to take two vectors and show the third one out as not a linear combination of the first two. Then you'd have to go to, say, V2, show V2 is not a linear combination of the others. It all just gets a little out of hand really, really quick if you try to use these prior theorems. Instead, for this situation, we would absolutely use this approach right here. In fact, that's the theorem that goes right down below it, because it's in a couple spots. The columns of a matrix A are linearly independent if and only if AX equals 0 has only the trivial solution. So we use this theorem right here whenever we have 3 or more vectors that we're dealing with. In fact, let's throw that in as a concept or a comment right here. Use this for 3 or more vectors. Okay, in fact, we're going to use it right away on the example right above. Okay, so we have definitely 3 or more vectors. If we're going to test the independence, we could form the matrix equation, or we could form a vector equation. But in anything that we do, we're eventually going to just start reducing stuff. And the reduction would be for this system right here. You may or may not augment. It's going to be up to you. I typically would not augment if all I'm doing is addressing linear independence. So here's how the strategy is going to start. First, take A and implant inside A these vectors. Now, one thing that's kind of an interesting strategy here is the order you put the vectors in the matrix A is irrelevant. It doesn't matter if I put V1 first in the list or last in the list. They're either all independent or dependent aside from their ordering. So if that's the case, sometimes you might decide it might be a good idea to put V3 first. That would arrange for a pivot without a row reduction. What would be the next best one? Maybe V1 will get the pivot in the right place. So V1 I'll do next. Next, I'll throw in V2. And what I'm trying to imagine is, what would these look like if they were arranged just right and suddenly in an echelon form? If you do a little bit of that look before you think kind of, or look before you leap kind of work there, you might not have to do any row reduction at all. So this is still equal to, let's read out V3, -1, 3, 1. And then if we went after V3, V1 is 0, 2, 3. And I really thought I had this in an augmented form, but I think I got it all slightly off. 0, 0, -8. We might have been done a little bit better there, but let's see. Let's just move from this point on. It kind of looks like I have it flipped. If I would have transposed this, it might have worked out. Let's keep doing the row reduction. I'm going to pivot off this entry right here. So copy a -1, 0, 0. Let's take and multiply this by 3, added below. We'll get 0, 2, 0. Next, we can take row 1 and just add it to row 3. We'll get 0, 3, -8. And my claim is you probably didn't have to work this hard, but here we are. It looks like I have a couple more row reductions to do. That's good practice either way. Any questions so far to that stage? Okay. Looking at the situation, we're all set here. We need to deal with this to get the 3 eliminated. So you might convert that to a 1. It automatically wipes out the 3 below. In fact, if this was an exam question, you're allowed to do this. I'm not going to do it in the notes. It makes the notes too confusing to read. But you might observe that you can just change that to a 1 and then multiply by -3 on row 1. Multiply by -3 in row 2 to row 3. That's now a 0. And that's okay if you take little shortcut type steps like that. We're pretty much done and we have a pivot in every column. But for the notes, because again, it's sometimes extremely confusing to read that if you saw that last step, let's just write this in to make it official. -1, 0, 0, 0, 1, 0. Now I'm going to take this row, multiply it by -3, add it to that row. We'll get 0, 0, -8. Now we have a pivot here, here, and here, and we're ready for a conclusion. What would you all say so far? Is this independence or dependence that we're looking at? Exactly. If we have no free variable because there's a pivot in every column, this is independence. You could write out your answer kind of like this. AX set to the 0 vector has no free variable. And this implies V1, V2, V3 is linearly independent. So we have independence of those vectors. That's quite nice. We'll see lots of interesting stuff we can do with that later on in chapter 4. But any questions or comments at all, folks, on getting through this one? Okay, maybe just a quick comment. This is not something I take points off of, but sometimes when you write down your work here, the way you write it can matter. And one thing we should avoid saying is this. We should not say A is linearly independent. That would be a different concept, a different vector space we're working inside. What we would want to say instead is it's the columns of A that are linearly independent, or you could just reference V1, V2, V3. So it's all about the columns, not about the matrix itself that the question is asking. Well, that's, again, really powerful theorem for us. On example 4, it's asking the same questions. Are the columns of matrix A linearly independent? Let's try it again on this one. Gives us a extra practice for this problem here. I think what was supposed to happen was if you arrange these vectors in a nice way, you didn't have to row reduce, but I messed it up. So here's the row reduction. And now we're going to row reduce again on this question here. Same question. We want to know if the columns of this matrix A are linearly independent. I guess there is some difference here because the matrix is already formed. And in the prior question, it was separating out the column vectors here. It's the same exact process, either way it's written. And so there's a slight variation on this example here. But the process pretty much goes like this. Take A, we'll reduce this. I should make a comment. This is only echelon form that we need because we just are looking for pivots, not a solution. So let's put in 1, 2, 4 row-wise. My first operation will be multiply row 1 by -2, add to the row below to get 0, -3, -9. Next operation, multiply row 1 by -4, add to the row way below, row 3, and we'll get 0 on this one. That's -8 plus 3, so -5. This will be, I forgot we were multiplying, -16 now, multiplied by -4 plus 1, so -15. There we are, folks. We have our matrix. And this one looks kind of suspicious. Divide by -3, we'll get 1, 3 here. Divide by -5, and you get 1, 3 here. If you wiped out this row, you're correct to do so at this stage. Row 3 is effectively gone. But let's show those steps. 1, 4, 2, 1, 2, 4. We're dividing row 2 by -3 to get 0, 1, 3. Then divide this row by, say, -5 to get 0, 1, 3 as well. So now we could copy it in row 1, 1, 2, 4, row 2, 0, 1, 3. And here's our next operation. Multiply row 2 by -1, add to row 3 to get all zeros now. At this stage, we have exhibited that pivots are here and here. So this is the moment of truth. When you're looking at that, is this independence or dependence? Good call. We've got a free variable, so dependence here. This would be a variable for x3 if we want to say specifically 1, but you could also just say ax set to the 0 vector has a free variable. This is the justification, the explanation. This part is the conclusion. This implies the columns of A are linearly dependent. And again, always good to say columns there. We're not saying A is linearly dependent. In fact, it wouldn't be. Well, any questions at all, folks, on that example 4? Okay, so that's what linear independence looks like, 3 vectors or more. This is the stage of the notes where we want to not always row reduce everything we find. We're starting to collect more and more interesting theorems. And here's the next interesting theorem that we can deal with once I get these notes in the right spot. Let's set it up maybe like that. There we go. So we have three vectors in this system, and we want to determine if V1 through V3 is linearly independent or dependent. But before doing any work at all, here's the thoughts you might have on this one. I'm going to use the orange pen. Imagine this is just a comment or something you're thinking in your head. The process was to take A and throw in V1, V2, V3. But notice if you did that, you're going to get a 1.7, negative 1.73, negative 1, and 1. Let's circle the best case for pivots on this. What's the maximum amount of pivots you would have in the system? Exactly, just 2. You might have one here. It might be here. We're not sure until we're probably there. We wouldn't be completely sure until row reduction. That leaves a free variable, and so we're pretty much done. This is what we might write down officially, though. Let me put this in orange. We would say probably that since there are more vectors than entries per vector, V1, V2, V3 is, well, now we can see it from two ways. Here, there is a free variable. They have to be linearly dependent. And that's a foregone conclusion, but you could have also said, you have 3 vectors, but there's just 2 entries per vector. Theorem 8 is on the table for us. It tells us that's guaranteed to be a linearly dependent set. There would always be a free variable, at least one, in this kind of configuration. So if you have more vectors than entries per vector, we have dependence automatically. And we're starting to get to some weird kind of information that ties this together. Why is 3 vectors linearly dependent in R2? Because R2 is too small to contain so many linearly independent vectors. You could say something along these lines. Let's say for R3 as an example. In R3, the maximum size of a linearly independent set is 3. Let's circle the massively important feature of that statement here and here. If you're working in R3, you cannot go beyond 3 vectors or else you are automatically linearly dependent. And this is what this is saying. More vectors than entries per vector is really the same statement as what we see up here. What's making all this work is the dimension of R3 is 3, and if you exceed the dimension with the number of vectors you're pulling in, it's automatically going to be dependent. It's kind of a foggy thought because we haven't defined dimension at all yet. We have an intuition that 3-dimensional space R3, that ought to be 3-dimensional. Well, any questions, folks, with this question here? Okay, now let's take a look at this last one here. My font converted into Calibri for some apparent reason. I think Microsoft is just trying to spread Calibri throughout the world for no apparent reason. We can always fix it though. And here's our next question. This time we have 3 vectors, so we might put that augmented set. Theorem 8 above is not even going to help us on this one. Let's move it away from Theorem 8. Definitely the next page. But before we start working on this one, I'll leave it up to the class. You can shout it out, throw it into the chat. Is this set of vectors dependent or independent? What you want to imagine is, what would happen if you put this into a matrix? Where would your pivots be? We have a chat, and Rajab says dependent. Awesome, thanks Rajab. Anyone else agree with Rajab? We have some in class also agreeing. And yeah, I totally agree. This ought to be a dependent set. Let's go through the motions of, here's the thoughts I might have if I didn't have a theorem available. Let's put this in orange. How would we approach this? It's three vectors, so we probably would just put them in a matrix. A would be V1, V2, V3. Once we write out that matrix, we have 1, 7, -8, -1.7, 3, 12. And here is the problem. That zero vector is going to cause us to have, for sure, at least one free variable right in this column. But the moment you have a free variable, the set of vectors is automatically dependent right at that stage. So for this problem, you can write out your whole conclusion by saying, let me get the right color. I'm trying to do green for dependence, blue for independence. AX equals a zero vector. This zero vector here is not referring to this one. This zero vector lives inside the matrix A, which means there's automatically a free variable. So has a free variable. This automatically implies the set of vectors v1, v2, v3 is linearly dependent. So that's the foregone conclusion on this one. But notice the fact that we had a free variable here is not a coincidence with the fact that we had the zero vector. It turns out if the zero vector is in your set of vectors, even if it's, say, the only vector, it's dependent. The zero vector is like the bad apple that ruins the set each and every single time. Even if it's the sole entry in the set, you've got dependence with that zero vector. And in our current problem, way down here, all of a sudden, there it is. The presence of that one zero vector, if you visually find it, you have the same situation. Linear dependence here, each and every time. And so that's our theorem 9. I think theorem 9 is quite a nice one to have at the ready each and every time. As soon as you contain the zero vector, just shout out dependence and you're always correct. There's lots of little theorems and things like that that you can throw in with independence and dependence. But this is on our notes going to be the full set of those kinds of questions and concepts. Well, any questions or comments at all, folks, so far? Okay, now since section 1.7, it will be on our first exam. I want to get a comment that this kind of question will be on exam 1. Since it's a short turnaround before getting to the exam, that's a decent hint to throw out there. Also, I think this is a good one to give us a little confidence because it's looks like a tough question. We're now thinking of every single definition and theorem we went through, and we want to determine by inspection whether our vectors are independent or dependent. It says here, do not use row operations. On a real exam, I'm not going to take off points if you did use row operations. Think of those statements as a way of me saying to you, you don't have to. There's a faster way. There's an idea or a theorem that means you will eliminate the need for row operations, making the question faster. And on a real exam, I wouldn't put this on here either. This is more for us in the notes and on the homework as well when we're learning this content. So as an exam 1 question, you're just going to say independent or dependent next to it, and then you're done. Let's do it as a class. So this will be a bona fide class activity. How about starting for folks in Zoom? In Zoom, would you call this independent or dependent as a set of vectors? Folks are saying definitely independent. Good call, folks. This one is independent. We can say independent since it's not the zero vector. So on the homework, this is pretty much all I'm asking for. On the exam, this is all I want. Just that overall conclusion. But let's keep on going through them. On the next one we're looking at, there are 2 vectors that we're dealing with. Now we have to decide, are they multiples of each other? If they are, that's dependence, and if they aren't, it's independence. Anyone see which one these should be? Independent or dependent? Absolutely. In fact, there's a pretty good giveaway here. If you have a row that goes 0, 1, and it's just two vectors, they are automatically not multiples of each other. It's impossible at this stage. And so we can write out they are independent. Let's write it this way. They are not multiples of each other. And so they are independent. So that's independence for two vectors there. How about folks on this one? Is that independent or dependent on part C? Rajab is saying dependent. How about folks in class? Do you all agree? Awesome. So looks like, yeah, this one would definitely be dependent. And the dependence of this set was because of that zero vector. Always watch out for a column consisting entirely of zeros. That zero vector has destroyed any possibility for independence of that set. So here we can say dependence or dependent, since the zero vector is in the set. So in that set of three vectors, the presence of the zero vector is the only thing that you need to determine dependence immediately on that one. And then from here on out, it honestly gets kind of hard to define or come up with a problem that's too terribly new. On this one, though, this is automatically, what would you all say, independent or dependent? Good call. This is the dependent one. And here's how we can answer it. Dependent, since there are three vectors. Where did they come from? They have two entries in total, so there are three vectors in R2. In other words, we have more vectors than entries per vector, and that's always a dependent set. Or again, you can imagine, put this in a matrix, it's going to be 2 rows, 3 columns. The third column, one of the third columns is automatically going to be a free variable associated to it. So these are always looking kind of weird. The more and more you study these kinds of problems, you're going to get really good at identifying the zero vector because that's a fast way to determine dependence. If it's 2 vectors, you're determining if they're multiples, but that's the giveaway. And if it's 2 vectors but looks like this, you know, it's a little bit trickier. One thing I can't do is abuse a 0 to a non-zero entry because the zeros lined up. But looking at it further, what does it look like? Dependent or independent on those two? Good call. This one would be dependent. And to you, what would you say is the major reason, just looking at it, that causes it to be dependent? Exactly. If you go through this row, looks like it was multiplied by 10. Multiplied by 10 here still works out. So that's automatically multiples of each other. So we'll say dependent. They are multiples of each other. So that's one exam question, faster than how we did it, since I won't ask for the justification. We have done that in the notes, and we'll do that in the homework as well. Well, any questions at all, folks, on getting through these kind of weird problems so far? Okay. Now that we've gone through the major content, here's one additional question that, to me, is a little bit wild. It says, let A be an n by n matrix. We're going to assume AX equals B has a solution for every vector B in Rn. Explain why the columns of A must be linearly independent. To me, this is kind of a tough question, but these are the kinds of questions that we want to become fluent with by the time we get through the course. You'll be able to see this and know just what theorem you have to pull in to walk through and get a good conclusion in. It's not necessarily a question I would ask on an exam unless we did lots of these kinds of questions in the homework. We might do a little bit of that when we're in chapter 2, but it'll be a pretty minimal part of the course truly. But before we get through this problem, anyone recall what theorem might actually help us? If it were a real exam question, what would you be thinking of?
The first one, where it says that there's, no free variables.
Or you're saying first one in which section?
Very beginning.
Oh, the consistency uniqueness theorem. It turns out it's not exactly that one, but you are on the right track. We need a theorem that talks about consistency, but has even more parts that goes along with it. So kind of a bigger theorem than even that one. Theorem 4?
That one?
I think you're on the right track. I forget the numbers specifically. Yeah, exactly. Right here. And yes, you're right. Theorem 4. Good call, folks. Turns out it's this one. It's not easy to tell, right? So let's put it in the problem, but also indicate what part of the theorem is really actually related to this problem. So here's theorem 4. Let's just inject it right into the notes. So let's take a look. A is of size n by n. That's kind of unusual already because that's a square matrix. You usually use this theorem when this matrix is not square, but n can be anything. It includes square matrices as well in this theorem right here. So we are okay on track with this. Assume that the equation ax equals b has a solution for every vector b in Rn. That's a heck of a statement, but that's just a rewording of that statement. For every vector b in Rm, ax equals b has a solution. So those two line up. They're the same concepts. Now that we know this is true, that statement is true, and so is all three other statements. We're looking next for the part of theorem 4 that's going to explain why the columns of A must be linearly independent. It's either going to be B, C, or D. Anyone see which part of the theorem we need to move to the next portion? Good call. It's absolutely part D. Part D is all about the pivots. And that's tied together with linear independence as well. If there is pivots in every single column, you don't have a free variable. So let's write out that next statement. We know A has a pivot in, now we need to be really careful with that. We really have to say every row as opposed to every column. So a pivot in every, let's not use blue though, has a very important concept here. Independence. I'll just use yellow again. As a pivot in every row. But then we can pause and say, there were n rows, and there's also n columns. It's a square matrix. The moment you said there's a pivot in every row, there's also a pivot in every column. Since A is square, let's say it this way, since A is n by n squared, there must be a pivot in every column. What does that do for us? If there's a pivot in every column, AX set to 0 has no free variable, you automatically have linearly independent columns. Really, this starts to become the more important concept. A pivot column, pivot in every column means all columns are linearly independent. In some strange way, this is a great way to organize linear algebra. It's all about the pivots if you're working R2, R3, and so on. So we can say here, there's a pivot in every column. Then AX set to the 0 vector has only the trivial solution. And so the columns of A are also linearly independent. So this is, again, kind of a strange exercise. We don't ask a lot of these, particularly not on exams. And once we do them on the homework, we'll do a lot of them on the notes to support the strategies on what we have to do to get through them. The reason we did them today is it's important to know Theorem 4 is tricky to use. It applies just about everywhere in the text. And it's not just about the concepts we see here. The moment you convert to a square matrix, having, say, the column span is equivalent to the columns being linearly independent, which means square matrices are very special. Spanning and independence, we throw together down here to form a basis for the vector space. Once we have a basis for a vector space, we can do other wild things with that vector space. We'll be able to do operations more effectively, define coordinate systems on it, and all sorts of wild stuff in chapter 4. So the bigger takeaway in this problem is square matrices are particularly important in linear algebra. Well, any questions, folks, at all with getting through this one? Okay, maybe one last thought while we're, have a few minutes to spare. I want to make one additional comment way up here. We looked at two vectors. One of them was dependent. The other set of two vectors was linearly independent. Then there's another way you could view this. Suppose you plotted these two vectors. Here's what it would look like. Here's 1, 2, -3. V1 goes there. And if you span that, the span of V1 is a line that goes to the origin. But look at V2. Plot V2, it's -4, up 6. Now, keep in mind, my hand isn't completely steady, but it turns out it would land right back on the line, V2. For two vectors, dependence means both vectors are in the same exact spanning set. But these two are completely different. These are on lines that are non-overlapping parallel. That's what independence would look like versus dependence graphically. Well, that's just an additional thought I thought I'd throw out there. Feels like we didn't talk about the geometry as much as the actual algebra. But any other questions or comments before we call it a night? Okay, well, have a great night, everyone. When we come back, we'll be looking at section 1.8. But if you have questions about the exam, don't hesitate to bring them to class. We don't have a formal review, but we can always do an informal one and address those questions. Have a great night, folks. I'll see you all Thursday. Sure.
Number 5 here, I can't seem to line up with the answer. I don't know if I'm doing my rail operations wrong, but I put it down to
Yeah.
I was doing something like that. But the answer is like -5, 2, and then 1 right here. I mean, I have to look at the thing again, the PDF, but I can't seem to get the answer line up the way that it's supposed to be because we're supposed to have it set like this.
Yeah. And with how we've got it, this would have no non-trivial solutions, or it's going to have a unique solution, just a zero vector.
Right.
Let's take a look. So 1, 3, 1, 0, -4, -9, 2, 0, -3, -6. And so multiplied by 4 looks like the operation.
I think that is what I did.
Yeah, that looks good there. Nothing to do on this one. Then say, I think maybe this is what might be an issue on it.
Okay.
Let's see. Multiplied by 4, we got that, and it looks good. But then we need an operation on this row to interact with that. Looks like you can add them together. 6 and -6. So this 3 and that 3 would give us a 0. This 6, -6 should give you a 0 right there.
Oh,
I think that's what the issue was.
Okay.
So yeah, adding that row to that entry should 0 that one out.
Okay, that makes more sense. Okay, well, let me ask this question too. I had a question on this. On number, let's see. Oh, wait. Number 11. I was setting up my equation here. Honestly, I don't remember exactly my questions. I was gonna have to look at the PDF. I probably should be more prepared with that.
Actually, I could pull that up right here.
Yeah.
Oh, sorry, I missed a chat, but I think we're all right. Which assignment was this one?
This was number 5.
Gotcha. So I just realized I could pull that up right here as well. Okay, we're looking at 11 on that one.
Yeah, so declare all solution based on parametric vector array is not really equivalent to the given matrix. So I'm trying to get this to, because it needs to be row reduced, right?
Yeah,
Yeah.
we need to eliminate that -2 to start,
Uh-huh.
and then that 3 eventually.
Which I do, yeah, I did eliminate number 2,
Awesome.
and then I did do that number 3, and I got these down. I guess maybe I had a question about set of the equation. Oh yeah, so is x6 gonna be a free variable, or is x6 just gonna be nothing on this when I set it up?
Let's see, we've got X1 is a pivot, X2 is free, X3 is a pivot, X4 is free,
That's, okay,
pivot, and then X6 is free. Yeah.
x6 is free, okay, so x6 is free.
Mhm.
And then when I set up x6 in the parametric vector form, is that what my question was maybe? I'm trying to think, what would the final form of this one look like?
Well, I like how you went X2 equals X2
Right,
for that free variable, and then X3 equals, what, that's X4. X1, X2, oh, X3. On this one,
that's x4 right here, right?
X4, yeah.
So my x3, I have it as x3 equals, because there's this one, right? Negative
Positive
right here.
X6, yeah, that looks
Positive
good.
x6, and x4, I put, oh, x4, that's right here. So x4, I put 0, but is that
That one would be a free.
that would just be free?
So you'd write
Okay.
X4 equals X4 on that one.
Okay, and then x5, I had it to the positive 4x.
Yeah, that looks good.
And then x6 would just be free as well.
Free as well, yeah. So
Okay.
X6 equals X6.
Okay, that makes more sense.
Cool.
All right, sweet. Those are all my questions then.
Sounds good.
All right, I appreciate it. Thank you.
You bet. Have a good night. Hello.
Hey, sorry, I forgot to do back homework real quick.
Oh, no worries. And I've been forgetting to hand back homework as well, so I think I probably owe me a sub. What was the name?
Scott?
Gotcha. Oh, and did you see my email about
I
those
did,
first assignments?
yeah. and
Awesome.
I actually put the correct ones on here.
Hey, perfect. Thanks. I appreciate that. And sorry for the inconvenience of that issue with the old text problems and stuff like that.
Yeah, no
Kind of
problem
a
at all.
nuisance.
Yeah, I misinterpreted the syllabus. I should know the questions were different, but
Gotcha.
yeah, sorry.
No worries. I appreciate you for getting these in. You too.